In this application video, we are going to demonstrate how online flow reaction monitoring of a Wittig reaction can be achieved using deployable mass detection, or better known as mass spectrometry. Mass spectrometry is an analytical technique used to determine the mass of a molecule by measuring the mass-to-charge ratio of its ion. Due to its sensitivity and selectivity, it is recognized as one of the gold standards of analytical chemistry, and as a universal detector, it provides confirmation, diagnostics, and helps to identify unknowns in chemical samples. For online monitoring of flow chemical reactions, mass spec can be used to analyze in real time the chemical composition of the flow stream in order to optimize transformations. It can monitor the fate of the starting materials, confirm the presence of the desired product, identify reactive intermediates and impurities, determine steady-state conditions of the reaction, and optimize transformation, improving yield, purity, and reaction selectivity. In this video, we report the online reaction monitoring of the Wittig reaction of nitrobenzyl triphenylphosphonium bromide with methyl formyl benzoate using the Microsaic 4000 mid mass detector and the Syrris Asia flow chemistry system. The online characterization of the Wittig reaction has been carried out by coupling these two systems together using the Microsaic Midas interface module. The time taken to install, connect these systems together and acquire meaningful data was less than an hour. The Wittig reaction of nitrobenzyl triphenylphosphonium bromide with methyl formyl benzoate results in the synthesis of the methyl benzoate. This Wittig reaction was analysed in real time, acquiring data in full scan with the mass spectrometer, using the positive tune file settings. The reaction was carried out under different flow reaction temperatures from 5 to 60 degrees Celsius using the following settings for the flow reactor and interface module. The expected reaction is for nitrobenzyl triphenylphosphonium bromide to be deprotonated by sodium methoxide, generating the phosphonium yellide, an intermediate strongly coloured in pink-purple. The yellide then reacts with methyl formyl benzoate to yield the methyl benzoate and triphenylphosphine oxide as reaction products. The reaction starts after loading the reagents into the flow reactor loops. The reactants flow from the loop to the microreactor, where a pink-purple coloration can be gradually seen filling the reactor from the bottom. The rate-limiting step of this reaction is the yellide reacting with the methyl formyl benzoate, and the pink colour therefore fades as the reactants reach the top of the reactor. Eventually, the reaction should reach the equilibrium, where the pink colour is the strongest at the bottom of the reactor and completely clear at the top. If the temperature of the reactor is increased, the rate of the reaction will also increase, and therefore the intermediate yellide along with its coloration visible on the reactor should fall. The mass spectrum of the reaction shows the reaction intermediate, product, and byproduct ions at a reaction temperature of 20 degrees Celsius. Typical sodium adducts of triphenylphosphine oxide and its dimer were also seen. Data from the mass spec can be used to show the formation of the product and byproduct as well as consumption of the intermediate as a function of reaction temperature. It can also be used to identify the optimum reaction temperature, monitor the intermediate and impurity generated in real time. The temperature profile was obtained in less than 2 hours from initial experimental setup. This significantly reduced the associated costs of offline analysis, which are usually more time-consuming. It is quite clear to see from these results that there are many great advantages to using miniaturized mass detectors for online reaction monitoring. When using the Microsaic mass detector coupled with the Syrris Asia flow reactor system, you can generate instant data used to determine unstable intermediates, byproducts, and monitor impurities in real time, allowing you to optimize the Wittig reaction, improving yield and selectivity. This all results in a decrease in the time taken for reaction optimization and is clearly apparent since there is no delay waiting for offline analytical results. We hope you enjoy this demonstration of how Microsaic's mass detector can be used in online flow reaction monitoring. If you are interested to learn more, please visit us at microsaic.com.